Hi guys, welcome to Petroleum Downstream Crash Course. Today we want to continue on our discussion of hydrotreating. So we want to talk a little more about the catalysts, the hydrodenitrification process, the aromatic saturation process, as well as some other patterns or designs. Okay, let's just take a look slowly, alright? In our last video, we actually talked about some of the hydrodesulphurization process. We basically have some feed that goes through a preheater into a fixed bed reactor where we have some powdered catalysts reacting with the hydrogen and the feed in this reactor. Thereafter, the hydrogen sulfide comes out because sulfur is extracted from the feed into the hydrogen sulfide. So in the fractionator, the separator setups, we will have the hydrogen and the the hydrogen mixture and the hydrogen sulfide mixture all separated, and the effluent from the reactor, the liquid effluent, which is can be on naphtha, gas oil, that will be fractionated out as well. And of course, if there are any minor cracking reactions that happen, that will be separated out in this fractionator. Okay. And additionally, what we have is some of the other reactions happening are that metals can organometallic compounds, which means the metals that are trapped inside the hydrocarbon structure, they are taken out and they're deposited into this reactor. Now the thing is that as impurities such as coke, because there's very limited cracking, as impurities such as coke and metal are deposited in this reactor, you'll have to replace the catalyst every once in a while. And of course, what we haven't mentioned is that yes, we can recycle this hydrogen, and we should, due to the reasons of cost. This wasn't actually elaborated a lot in the was this elaborated? I think so, right? This wasn't really elaborated in the last video, but if you can separate out some of that hydrogen, you can recycle it along with your feed. So you can have H2 feed here, the fresh feed. That will be this H2, this hydrogen will be mixed with some recycle stream, and that will come back and be mixed with the stream here. All right. So that's more or less the generic kind of hydrotreating process. And when we talked about the catalyst of this process, we actually talked about the cobalt molybdenum sulfide. And we tend to think of them as full particles, right? Full particles of cobalt molybdenum sulfide just acting as catalysts. But the thing is, if you zoom in on one of these particles, let's zoom in on one of these particles. So this is an enlarged picture. All right. This is an enlarged picture of the cobalt molybdenum sulfide catalyst particle. We'll notice that only the atoms at the surface are doing all the hard work of catalyzing reactions. As you can think of a Lego model or space filling model. You can imagine, let's say I have a fist here. My fist is this catalyst particle, and this is the hydrocarbon you want to get the sulfur out of. Now, in the center of my fist, the pen cannot reach the center of my fist. It will only touch the outside of the fist. And likewise, the hydrocarbon will only touch the outside of the catalyst particle. So surface area is very important, and only the catalyst particles at the surface are doing all the hard work. These guys are just lazing around doing nothing. And you don't really want that in a refinery because these are expensive. I mean, these have associated costs, and you want to reduce you want to reduce all these costs as much as possible. So what is being done? Instead of having the center guys being the cobalt and molybdenum, they use something a little cheaper. Let's say a mixture of silica and alumina, or you can use either one on its own to be the central core of this catalyst. So they have particles of this, and they'll coat it with a little bit of cobalt molybdenum sulfide. Of course, there are pros and cons. As you well know, for those who study chemistry, you know that this can be a very acidic combination. So this can contribute to some of the cracking processes. As such, it contributes to the cracking that happens here, and it kind of makes, increases the gas production so that you have to separate a little more in your fractionator. So that's a bit of pros and cons. So we have already talked about the sulfur and metallic impurities that have been removed, and we know that for sulfur compounds, we remove it using cobalt molybdenum sulfide. However, there are other impurities as well, such as nitrogen. Nitrogen here, we have to remove because of environmental regulations. It can make nitrogen dioxide. And to remove it, all we have to do is to simply replace the cobalt with nickel, right? Using a cobalt nickel catalyst. And the other so-called impurity we want to remove is the aromatics, because we have specifications on how much aromatics we can have. So we have to remove some of that aromatics so that our products are on spec. And the way to measure it is usually by measuring something known as a pour point. If you're not sure what the pour point is, you can go look it up. Yep. And in fact, that'll be a good piece of homework for you. Okay? Tell me what the pour point is. Post it in the comment section below. Alright. Now, to reduce the amount of aromatics, we can do something called hydrogenation, which is to add hydrogen to unsaturated hydrocarbons. And if you study chemistry, you already know that benzene, aromatic compounds such as benzene, are relatively unsaturated. They have a very low hydrogen to carbon ratio, and that can produce very smoky flames, and that's not very desirable. So to do this, all we have to do, if you want to do an aromatic saturation, all we have to do is to add nickel into our mix of metals. So we have our central core, the central core of silica or alumina. Then we coat the outside in nickel and cobalt molybdenum sulfide. Okay? And the HDN process, hydrodenitrification, we just use nickel and molybdenum sulfide. However, doing so will result in this following problem. We will actually generate ammonia as we do a HDN process. So hydrogen will react with the nitrogen inside the hydrocarbon and produce ammonia. So instead of just having hydrogen sulfide to deal with, you have to deal with ammonia as well, which you will have to kind of separate in this separators, this series of separators. Okay. However, as for the aromatic saturation, you can see from this reaction that there's no other kind of problem, except that it kind of reduces the octane number. So we don't have any kind of unwanted gases we want. However, we have to control the amount of arosat that we perform, because this, which is cyclohexane, has a lower octane number than benzene. And for gasoline, you want to control that so that your fuel has a high enough octane number and it balances with the amount of aromatics you can have in your compound or in your gasoline, according to the specifications, of course. Okay, so that's more or less it for the catalyst, the hydrodenitrification, and arosat reactions. However, as you can see, for different fractions of the refinery or different fuels you want to produce, there are kind of different specifications for each kind of fuel. So in naphtha fraction, you will have to look out for the octane number. For gas oil, or diesel, you will have to look out for cetane number. For cetane number, you generally are okay with hydrogenation because it makes it easier to ignite and that gives it a higher cetane number. For kerosene, you are caring a lot about the smoke point and the pour point, which is the amount of aromatics. So you want to make sure that for kerosene, arosat is a very important thing to take note of. For residue, that's a whole different ballgame altogether. I'm not going to talk about it in this video. Okay? So yeah, for naphtha, you have to take care of the benzene and cyclohexane, the kind of a balance. Alright? And here's a homework for you. Go and find out the octane number, the research octane number, the run number of benzene and cyclohexane. Okay? Now other than that, why would you want so many kind of different processes and so many different catalysts? The thing is that you want a selective process because you don't want to waste. You want to save on your hydrogen requirement. You don't want to waste hydrogen because hydrogen is an expensive process. And of course you want to, especially for your naphtha fraction, you want to control how much arosat actually goes on. So you want enough of those benzene molecules so that the octane number of the fuel actually is at a desirable level, but you don't want too much because of the aromatics and benzene specifications. Okay, so there are a whole host of ways you can do this. So one of the ways is to cater the reaction conditions for each of these processes and each of these streams. So for naphtha, the naphtha stream, we generally have hydrotreating processes or hydrodesulphurization processes with a pressure of 13.8 to 51.7 bar. So these are just some of the reaction conditions, right? So the temperature is from 290 to 370 degrees C and the linear hourly space velocity, the LHSV, is about 2 to 6 per hour, or liquid hourly space velocity is 2 to 6 per hour. Now these are standard hydrotreating conditions, but how does it differ from, let's say, a gasoline or kerosene hydrotreating process? You can see that the pressure increases. So you have to spend more energy to force that hydrogen into each of these molecules. Not only that, the temperature increases and the liquid hourly space velocity also decreases, meaning to say that the gasoline or kerosene will spend more time in the hydrotreating reactor. And for residues, the whole different ballgame, even more severe. Higher pressure, higher temperature, and lower linear liquid hourly space velocity. Okay? So we can see that to cater to each of these different streams, we have different processes or different process conditions, and especially for residues, you probably have a whole different way of hydrotreating the residues because this stuff is so sticky. Okay, so these numbers, and you can read more about this in this paper. So these numbers are from this paper. It's called an overview of new approaches to deep desulfurization for ultra clean gasoline, diesel fuel, and jet fuel. This is done by Song et al. Song, and this is done in 2003. So this is a citation, okay? And just to give you a flavor of what actual hydrotreating process or hydrodesulphurization process looks like, we have ExxonMobil's SCANFining process. Again, all of these brochures, these diagrams, I can show you where the websites are from. I'll post it in the comment section so you don't have to worry about where to find all these things. Okay, so let me explain to you this SCANFining process. First, you have a feed, which you mix with hydrogen, and you send it into a preheater. And this is a pre-treat reactor. And after the pre-treatment process, it goes into a second maybe heater or heat exchanger, and it goes into the hydrodesulphurization reactor, the main reactor. And after that, you'll probably be cooled down and you'll be separated so that the ammonia and the hydrogen sulfide and the hydrogen will be separated from the rest of the naphtha and other gases. So this is the naphtha and the other gases, which will be separated into the light ends and the heavy naphtha, the low sulfur naphtha. And the gas mixture, some of it will be purged and some of it will be mixed with fresh hydrogen. Goes into a compressor to increase the pressure and will be mixed with the feed again. So this is quite similar to what the basic process, the basic design process that we have talked about earlier. However, there's one key difference. You might be asking, what is the purpose of this pre-treat reactor? Alright? So I want to answer that now. So this pre-treat reactor, we can actually see this in patent US 765-1606 B2. I put the link again in the comment section. Oh no, not comment section. The description section below. This was done by a couple of inventors you can read on the website, and it was assigned to Institut Français du Petroleum. I'm not sure how to pronounce that. I'll just put in the link below. But this pre-treat reactor has a temperature of 80 to 220 degrees C, liquid space velocity and pressure. You can just read it off here. Well, why does it happen? Why does it have to occur? Well, we find out in our hydrotreating process that we have double bonds within our hydrocarbon. And double bonds are particularly annoying because they can react with other mercaptans. These are thiols, which are, these are like alcohols, except they have sulfur instead of oxygen. So mercaptans can be added to double bonds to form bigger compounds. That may or may not be good. Anyway, when you react this compound with hydrogen, it will separate out into the pentane and the propane. Excuse me. However, there's one other thing that can happen. When you have a double bond, you add hydrogen sulfide. That can result in formation of a mercaptan. Meaning to say that after you hydrotreat, right? After you hydrotreat the process, let's say you have a compound like this, you take the sulfur out and you produce hydrogen sulfide. If there are still other double bonds inside the product, the hydrogen sulfide can react with this double bond to form a mercaptan, which kind of defeats the purpose of you hydrotreating in the first place, because you're adding the sulfur back into the oil. Does it make sense at all? No. So what is being done in this pre-treat reactor? The idea is to saturate all these double bonds with hydrogen. So you want to add hydrogen to these double bonds first, right? You add hydrogen to these double bonds so that this reaction doesn't happen at all. So that's what the pre-treat reactor is for, is to saturate all the double bonds. And once the double bonds are saturated, then the hydrodesulphurization process or the hydrodenatrification process can begin proper. So over here you have a hot mixture of H2S and other oily products, right? And without the double bond, this process doesn't happen and your products will be low in sulfur. So that explains why you have to have these, and typical hydrotreating processes are like this. It's just that the process temperature and pressure may be different. And the space velocity may be different as well for the different kinds of processes for treating different kinds of fuels. And just to tell you, you know, for your own reference, you can look at other patterns for hydrotreating of different, different petroleum streams, different refinery streams. For naphtha hydrotreating, you can go and look at pattern US 5597476A. I'll put all these, I will give to you in the description, so don't worry. Gas oil, US 6217748B1. And this pattern applies to, you know, naphtha and gas oil, because the process may be quite similar. You can see lots of other design patterns as well. This one is US 4990242A. And for residue, probably you have different design considerations because of the stickiness, the viscosity of the fuel, and probably the sulfur content is higher. So you have this pattern US 3830731A. Now these are just some of the patterns. I'm not going to discuss the patterns. I only discuss the most important points. These are for your own further reading. And that's about it for this video. Thanks for watching. Please like, subscribe, comment, ask any questions you want, and post your homework in the comment section below. See ya!